Good afternoon. Let's try again. Good afternoon. Thank you. All right. Well, my name is Arun Gupta, and I'm glad you chose my session to attend the conference today. I know there are a lot of parallel tracks running, so thank you very much for attending my talk. We'll talk about how do you refactor your existing Java EE application using microservices and containers. Wow, there's a lot of buzzwords, huh? So my goal here is to kind of hopefully put some positioning around what we think microservices are, and how do you take an existing Java EE application and run them as microservices, or you refactor it into microservices. Now, as part of using them as a microservices, they're all different applications running. So how can containers fit into that entire picture? So that's sort of the thought process over here. I'm a practitioner myself, so I like writing code. So everything that I'm going to talk about is based upon code experience, so that you can learn from it as well. I work for Red Hat, natural. I'm the director for developer outreach. There are lots of ways to reach me. Twitter handle, my blog. Literally 10 minutes ago, I started writing a blog where I will not only share the slides, but I'll also write a little bit of more my thought process on what I think we should do around microservices and stuff like that. Or you can shoot me a mail, arungupta@redhat.com. Let's take a look at existing monolith application. By monolith, what I really mean is an application where all of the functionality is packaged into one application. Think of a movieplex application. Let's say you're running a cinema theater, multiple movie theaters. You need to book a ticket, add a movie, accrue the points on the movie tickets, and so on and so forth. That's a significant chunk of functionality. You can package all of it together in a WAR file. That's about it, right? And for each functionality, you have a UI layer, you have a database layer, you have a middle tier, you have these different layers, and you package them all together. So here is my UI, here is my database persistence layer, here is my business logic. There are different ways by which we accomplish these, but a classic way, specifically in the Java EE land, is you have HTML, CSS pages, could be XHTML if you're using JSF, for instance. Typical database interaction is using JPA, or you might be using Hibernate for that sake. In terms of business logic, again, lots of different varieties. But what I'm showing you is a very classical Java EE structure on how do we see these monolith applications to look like. But for you, for a container or for Wildfly application server, which is a Java EE 7 compliant application server, this is one WAR file. It doesn't care about what's inside it. It says, let me take it and run it as a single application. And that's what makes it a monolith. Now you can scale this application, you can run multiple instances of it. Wildfly can be configured to run in a cluster, or JBoss EAP can be run in a cluster, so you can run it that way. You can front end it with a load balancer. Very, very classical scenario here. That WAR file may not necessarily be just a WAR file. It could be an EAR file. That's an alternative packaging. So remember, I'm using yellow for WAR, and I'm using gray for EAR file. And by this, I mean the black border around it. I mean that's sort of the boundary of where, or the scope of my archive is, whether it is an EAR file or a WAR file. Same thing, I have an EAR file. I could have multiple instances of it, front-ended by a load balancer, own cache, own database. Very classical, very simple, dumbed-down architecture. There are several advantages to this architecture. Well, we have all been using it for a few years now. So your monolith application is typically packaged in a single EAR or a single WAR file. That makes it very, very IDE friendly. So tools like NetBeans, Eclipse, IntelliJ, they all understand, oh, this is an EAR file. I know how to generate this. Maven archetype, etc. All those are available. It generates it. You can edit it. You can debug it. Lots of advantages like that. It's very easy to test, because once that WAR file or EAR file is up, because everything is part of that archive, all the services that you need, so to say, are up. Your persistence context is loaded, your EJB backend is up, maybe lazy loading, but at least it's up, or when you ask for it, it's going to be up. You know that for sure. Things like that. So that's the monolith application. That's the nature of it. It may take some time to load up, but once the archive is up, it's up and everything is ready to run. And these are very simple to develop, because we have followed these. Simple is an overrated word, but at least we know what the issues by building these monolith applications are. Okay. Let's take an example. What are the issues with this classical monolith application? Well, I have a simple application. Version 1 is live. Version 2 comes out where I change a certain component of my application. But because this is a monolith, I got to rebuild my entire archive and drop that entire archive in the application server. There comes version 2. Even though my UI, my database, none of that concept is changed. Or maybe I just change one functional component of the app, but still, I need to redeploy my entire WAR file. Version 3 comes, I may change something in the UI layer, or again, this UI may be of a functional component, but you still have to redeploy the entire WAR file. Once again, so if anything changes in a monolith application, there is no way for you to say, oh, by the way, just redeploy only that particular part of it. Nope, you got to deploy the entire WAR file, and that's when the new version goes live. So with that, what are the disadvantages of a monolith application? Well, they are difficult to deploy and maintain. God forbid if you're using Spring, your WAR file is going to be 100 megabytes. So that means it's going to take a while to load that Spring WAR file. With Java EE, we have skinny wars at least, so the WAR file gets loaded fast rather. But if your WAR file loading time is bigger, that means it's going to take a lot longer to have more frequent deployments of your WAR file. Specifically, in an agile world, you want rapid deployment, more frequent deployments. But if you have to really deploy your WAR file and go for a coffee and come back and make sure that is up, that's not going to work. The other one, which I talked about, is obstacle to frequent deployments. You want to be, at least if you're doing a CI build, if you're running a deployment pipeline, so to say, you want to make sure the entire deployment pipeline is running under a few minutes. But if few minutes is just your deployment to one test environment, it's not going to work. No, it's not going to scale. It's going to be a big obstacle. The other significant part of a monolith application is like when you design your monolith application, like let's say this is Java EE application, you are stuck with that technology stack or framework, whatever you choose, Spring, whatever you chose, or application server you chose, because even though you say, yeah, it's a standards-based application, but eventually you start getting into the proprietary APIs, descriptors, etc., management, all those things, and you build your infrastructure around it. So what that means is, you have been building your application over 3 years. This new latest, greatest technology comes up. I can't change because my DevOps guy is not going to let me do it, or my ops guy will not support it, stuff like that. So that makes it really hard to try new technology. You might be the expert at Java EE, but you want to still try out a piece of a functionality, but then you have to extract that functionality out of your monolith and then go from there. So some of the issues with a classical monolith application. Here's this beautiful book called as Art of Scalability. This book talks about how there are 3 axes on which software can scale. There is a x-axis, there is a y-axis, and there is a z-axis. Okay, so here, x-axis is where it says horizontal duplication. So you want to scale your application. It's straightforward. You just have multiple instances running. You do. This is what we have been using all along. You can do that. Z-axis is where it says, oh, I'm going to do sharding, database sharding. So if requests come from Europe, I'm going to use this particular DNS server or database server. If Europe comes from US, I'm going to use this, and so on and so forth. So that allows your application to scale to an extent. The most interesting part here is the y-axis split, which is the functional decomposition, where it says you start functionally decomposing your application. And we'll talk about that in a second. But that's what the focus of the talk today is. And that's, if I were to say, like, describe microservices in like just a few words, like 3 or 4 words, I would just rather use two, which is functional decomposition of a service, or functional decomposition of a monolith application. That really, to me, is the essence. Everything else goes down, like, so 50,000 feet view for me, for a microservices, functional decomposition. Everything else, then you start digging deeper, like, 45,000, 40,000, so on and so forth. And then you start peeling the onion and getting more details. So Martin Fowler, is the guy who has sort of coined the term, and he's been talking about it, what really microservices are all about. So he says really microservice is basically a suite of services. Instead of one big application, build it as a suite of services. They're all independently deployable and scalable. So that means once you have a service functionally decomposed, hold on to that thought, once you have that functionally decomposed, each service can scale independently as x-axis or y-axis, because z-axis, well, I'm sorry, x-axis and z-axis, because y-axis is functionally decomposed already. They have very clearly defined interfaces. Each service, because is running independently, there are defined interfaces like REST-based services. They can use whatever programming languages they want to, and each service is typically managed by different teams. So let's drill down on each of these points and see what does it mean in our context. This is not the mantra that we want to say, that every couple of years a new technology comes up, and then we say, you know what, I'm going to refactor everything that I do using SOA. Now I'm going to do a refactor everything using REST. Now I'm going to do everything using SOAP, or I'm going to use everything WebSocket for it. So don't think microservices is sort of the golden bullet or the panacea for you, that everything you're doing, just drop it and just jump onto microservices. Not true. So instead of talking about, we sort of looked at the brief definition for it, and let's look at the characteristics of what a microservice are. Well, first of all, it's a domain-driven design, and that's what I mean by saying it's a functional decomposition, decomposition of your application. So let's say, go back to the Movieplex example. I have a booking functionality. I have adding a movie functionality. I have accruing the points functionality. So you define what your domain is, and that way there are very well-defined principles of domain-driven design. So that goes as part of it. Now, because you are looking at a domain, the typical way your teams are distributed are, oh, this is a UI team, this is a database team, this is a middleware team, and then they focus on their area, and then they define interfaces between them. Here, because you're doing domain-driven design, you're going with a full-stack development team. By full stack, I mean is, in that functionally decomposed team, like 8 to 10 people team, for example, you define what your UI layer is going to look like. You define what your middle tier is going to look like. You define what your persistence layer is going to look like. You have the full stack. Okay, and we're going to talk more about that in a second. Each service is very explicitly published on an interface. Now, the most common way of publishing that interface is REST endpoint. So you say, here is my REST endpoint, where my service is available, and it has a bounded context, in the sense you define the service is, this is the interface and this is the payload, and that's how I'm going to communicate with you. In this payload, I can expect either JSON or XML or YAML, whatever that data format is. We talked briefly about how each service is independently deployable and automated. So you can take down a service, you can bring up a service, you can upgrade the service, you can extend independently on any level. These services are truly decentralized. So these services, for example, if we think in terms of Java EE, are possibly multiple WAR files running around in your network, and they are using IPC mechanism. IPC is a very remote term. I mean, it's a really old term, but really, effectively, what we're saying, we use something like a REST endpoint to communicate between them, where they say, okay, these services are communicating with each other using REST terminology. Another key concept which we talked about is how you are not tied to a particular framework, because you are using a predefined interface, say a REST endpoint. The other service which is consuming the interface really should not care about what's the implementation level detail. So today I might be using Spring. I don't like it. I can just say, just get rid of it. I'm going to migrate complete thing to Java EE 7, and that's how I'm going to use it, as long as I maintain the contract and the interface and the payloads and all those things. Because effectively, to other services that are running with it, that's what matters. Everything else, it should be within that team. So tomorrow a new technology comes up that gives you the ability to try that new stack for your particular service. Another key part of this is, and this sort of kind of summarizes all of these, is how REST interface is so critical. Back in the SOA days, another name for microservices is called a SOA for hipsters, or SOA 2.0. People say call it all sorts of names, but there were some fundamental issues why SOA did not really got broader adoption in the developer community. It was more sort of on the ops community and things like that. But here is gaining big traction. Microservices is gaining big traction in the developer community. Now, with SOA came the concept of enterprise service bus, which was applying complex algorithms and logic on how do you transform the data, make them communicate from one point to other point. In this case, endpoints have the business logic. The pipes are dumb. Dumb as in HTTP dumb. You just send the data over it and it just transmits the data to the other side of it. And the endpoint, which is generating or consuming the payload, understands it and then deals with it. Another very critical, I mean, if you look at Netflix, at a given point of time, in the US, like Friday night or Saturday night, 33% of the internet traffic is by Netflix. That's a lot of traffic. That's a lot of bandwidth. About 2 years ago, I read an article. I read the article recently, but the older data is, on a given day, Netflix gets 2 billion calls using APIs, partners, etc. Each of those calls gets translated to 6 to 12 calls within Netflix itself. Netflix is running all on Amazon. They have 3 zones. One is, and all 3 are hot. So imagine running on Amazon, so many billion calls is bound to fail. It's 100% bound to fail. So that's where it says fault tolerance is a requirement, not a feature. So you have to build resiliency in your services, that if you are building microservices, what if you try to connect to the service, it's not responding? Is it timing out? And there are different patterns that I'll talk about in a second. But Hystrix is a library, for example, that allows you to build a resiliency very nicely in your microservice architecture. I don't know, how many of you know Uncle Ben from Spider-Man? Yeah. So he made this excellent comment which says, with great power comes great responsibility. Let's go back to the classic use case of Netflix. Now, with Netflix, at a given point of time, Netflix is a very classic story for microservices in that sense. In Netflix, any developer is free to push out any feature at any point of time. It's completely up to them. Okay. What that means is, at a given point of time, it's a self-provisioning environment. They can go to the Netflix dashboard or internal dashboard and say, provision 100 instances of Amazon here, push my feature over there. Then they do canary testing, and then they do A/B testing, and then they go live. But it's completely self-provisioning. Now, they know if the feature breaks, they're going to get a call, and they will have to fix it. They are responsible for maintaining it. The key concept being, you build it, you run it. Now, if you build it, and you know that, hey, there's an ops guy sitting on the other side who's going to take care of it, I'm not going to get a call at 3 a.m. in the morning. You'll be less careful about it. But if you know you possibly might get a call about it, you will be damn careful about it, because you don't want to get up at 3 in the morning. You don't mind the ops guy getting 3 in the morning. So I think this is a very fundamental requirement for microservice. The service, if you think about it, the concept of microservice, DevOps, containers, kind of all linked with each other, but we're going to focus on the microservice aspect of it. So another Conway principle, which is very, very important for microservices, where it says your organization will design an application which will mirror its communication structure. So, and this is sort of the biggest fundamental change that is required for microservices to get ready. When I talk to customers all the time, I was talking to a customer in Berlin earlier this week, and they are trying to take an existing monolith application and converting it into microservice. Their teams are classically designed as UI, database, middle tier, and that's how their applications were working. So far, so good. But they felt the need for doing microservice because they want to have the flexibility, more frequent deployments, stuff like that. So they literally had to change the team structure. That nope, you're not a UI team. They literally had to go through the entire organizational structure change in order to adopt microservices architecture. And that was, I asked him, in order to convert a monolith to a microservice, what was the biggest challenge? And he said that to us was the biggest challenge. Technology, everything else is a detail, but that to them was the biggest challenge, where they had to completely reshuffle their entire team. So what are the strategies for, I mean, you have a monolith. How do you decompose it? You start putting each function in a separate class and say, that's my microservice? Not true. So there are some, at least based upon our experience, there are some well-defined patterns, well-designed architecture, which have been tested to some extent. Let's take a look at that. Well, as I said, functional decomposition is my two-word definition of microservice. And also the very important part is, you look at, this is going to be my checkout functionality. This is going to be my product functionality. This is going to be my catalog functionality, so on and so forth. So you look at that aspect and say, this is my product microservice. This is my catalog microservice or checkout microservice. And then they talk to each other. You can use a noun. So as I said, catalog product service. Unix utilities are a beautiful example, something that we have been using forever. And they're a beautiful example of how microservices should be designed. Now, think of ls. Ls is a command. It's a single responsibility principle. What that means is it does one thing, and it does that one thing damn well. It does that really well, actually. I mean, I know the options are very confusing sometimes, with lots of options. But if you type ls, it'll type all the directory listing. If you do cp, if you do mv, each of those utilities of Unix, they do one thing, and they do that one thing very well. Now you can start piping them, and that's what we're saying. Hey, we are actually making those microservices work with each other effectively. So I think they are a very classical example of how microservices should be designed. So how do we start moving towards microservice then? We talked about a ER file with a bunch of WAR files, a bunch of jar files in there, their own cache database. So as I said, functional decomposition. If you want to go back with one message, think about functional decomposition. That's the message you want to go back with. Now here in my ER file, which is scaling, all that stuff, I recognize, oh, this is this WAR file, because ER has multiple WAR files. I can recognize this WAR file. This makes sense, actually. It could be, all it is basically a bunch of REST endpoints. I'm going to extract it, put it outside the ER file. These are possibly hosted in the same Wildfly or JBoss EAP instance, and that's fine. That's sort of to begin with. Now the advantage is, because these two are possibly running in the same EAP instance, JBoss instance, you can scale them independently. This will possibly have its own cache and database, because this is a REST endpoint, possibly pushing out some data as a REST service. Okay. In terms of load balancer, this application might be calling all of these services directly, or you may even expose this service directly to the load balancer itself. The second pattern that we see is, okay, let's say there are 3 services running. Once you have done the functional decomposition, and I'll talk about functional decomposition using a live example that I've been playing around for the past few days. Now, let's say you have functionally decomposed. You have service A, service B, service C. They will each optionally have a own cache and database. Another big challenge typically that we have seen, when I'm talking to customers who are migrating their monolith to microservices, in a monolith architecture, this database is all common, right? This is one big lump of database. When you're going microservice, the strong recommendation is each service is completely independent. They have their own database. So how do you refactor your database? How do you normalize or denormalize a database like that? It's not going to be easy. And if you do denormalize or normalize, then you have to start replicating data, so your overall size grows up. So I think that's another challenge that we have seen in terms of refactoring. But anyway, once you have service A, B, C, each having their cache and database, possibly optional, your load balancer, which is where your client is coming in, it could talk to an aggregator service, and all it's saying is, oh, you know what, I understand. These are the 3 services that you need to talk to. These services, they could be an internal detail. To the client, all you expose is aggregator service. Now that aggregator by itself could scale also. So that's sort of a microservice architecture or design pattern, you may say, we expect to see. And I'll show some samples of that. The other one is, in that case, a proxy pattern, where each service, again, is scaling independently on X or Y axis, X and Z axis. They have the cache and database. And all you're doing is you are setting up a proxy to these services. Now, in this case, is not really aggregating. In the previous case, it was pulling the response from all 3. Here, you're calling a load balancer. This is like your case of your sharding. So So you could say, oh, I'm going to call this service because this service talks to Europe zone, this service talks to US zone, this service takes care of the rest of the world. So you could start proxying based upon a certain parameter in this case. Another pattern that we have seen is called as a chain pattern. So here, your client goes to the load balancer, it talks to service A, there are service B and C, and then service A talks to B, talks to C, and then accumulates the result. From the client perspective, again, your interface is service A. This could be an internal detail. These might be exposed directly to the load balancer as well, if somebody wants to call them. So just a design pattern. Another one is a branch pattern, where you call service A. You could then, based upon some business logic over there, you could call either service B, which is running in its own environment, or you could call service C and D, which are again in a chain pattern. So again, very standard practices that we see happening, but this is like a branch pattern. Now remember, in this case, they have their own independent data. You could possibly have a shared data here, depending upon if they're running in the same container or not. So here you have the shared data between the two. Another design practice that we see is how, well, if you're using HTTP as a messaging pattern, that's what was being used in the previous design pattern so far. HTTP inherently is synchronous, or HTTP is synchronous. Because it's synchronous, it's gonna be a blocking factor. So then, to work around that, what you start using is asynchronous messaging. So here, you're calling load balancer, this is calling service A, and then all these different services are generating and consuming messages from a queue. So then you're using a messaging pattern over there. We've talked about a lot about microservice, but let's see, this talk is about microservice. So let's see what are the advantages of microservices. Well, they're easier to develop, understand, and maintain because Amazon has this culture of two-pizza team. That means a team should be big enough so that it can be fed by two pizza. Either the guys need to eat less, or the team should be small. The recommendation is, anywhere from 8 to 10 people. The size of the pizza could matter as well. I love the pizzas here, so they're very thin crust. Just love it. So it says advantages of microservices are because it's a two-pizza team. So you're looking at 8 to 10 people in a team. As a full stack team, those services, you will hopefully have a better communication, better coordination among those developers. So they're much more easier to develop and maintain. They definitely start faster than a monolith. As we said, monolith could be a much bigger WAR file. Here, it could be a much smaller size. And who knows, it may not even be a WAR file. It could be a completely different technology since we are not tied to a technology. A local change can be very easily deployed. So we are not going into the concepts of continuous deployment, but this is definitely a great enabler, how continuous deployment can be done if you're doing a microservice-based architecture. Each service can scale on x-axis, and this should be z-axis because y-axis is functional decomposition. That's a typo here. So each service can scale on x-axis, which is you run it multiple instances of container in your environment, or z-axis, which basically says, or z-axis, which says, oh, you know what? Now I'm going to do sharding. So each service is independent of that. It definitely helps you improve fault isolation. How many times you see, you go to a JSF page, you see exception track trace, and this like 4 level of nesting that's happening. It becomes nasty. At least to me, it becomes nasty. It's very hard to debug it. I just throw the application and write it all over again. In this case, because you are using a microservice, you know where the error is coming from. Hopefully, the code base is not that big, so it really simplifies, at least somewhat simplify on how you can do the fault isolation. And the key part is because you are focused on an interface on how and what the context needs to be, you are not really committed to a technology stack. I know it's not an easy task, but at least with 8 to 10 people, imagine a big monolith application built by 100 people, as opposed to a microservice built by 8 to 10 people. The changes you can imagine yourself is much easier to implement in a microservice-based architecture. Another key part, as we said, is just because you're building a monolith, the whole team has to tie into a particular technology stack. In this case, that's not a requirement. It doesn't mean that every time you take, you see a square peg and you try to jam it into the round hole. Now, so refactoring, is fun, but just the fact that your monolith is like a spaghetti doesn't mean you can actually start refactoring it into a well-designed or a microservice itself. So there are certain fundamentals that are required for a well-designed monolith itself. Make sure you don't have 500 classes in a package. So things like those. Make sure the packages themselves are functionally decomposed. That's what allows you to start refactoring your application into a microservice-based architecture. I talked to a customer once, a few years back. Their entire website was one JSP. The entire MVC is possible. He did it. Yeah, I just jammed the Java code in there. I do the transactions in there, some 50,000 lines of JSP, and boom, that's it. And that's a big monolith. Imagine refactoring that into a microservice. That's going to be a lot of challenge. So let's take a look at a classic example. Here is a Java E7 application. Now, this is a Java E7 hands-on lab that has been given all around the world. This is what I designed when I was at Oracle about 2 years ago, 2.5 years ago. So this is a Movieplex application. I got user interface. Look at the functional aspect of it. User interface, show booking, add, delete movie, ticket sales, movie points, chat room, etc. They're all taken to the same database. Okay, that's a very classical monolith application. This is actually packaged as a WAR file. In terms of interfaces, we're using JSF and JavaScript here in the front end. For REST, we're using JSON, and we're using all sorts of technologies here: EJBs, Batch, JMS, WebSocket, and JPA for all the backend connection. So very typical Java EE application. This could run on Glassfish or on Wildfly, or this won't run on JBus EAP because that is not Java E7 compliant yet. Now, the way I would package this application, I would have a WAR file. Remember, yellow was the WAR color. So I'll package this in a WAR file. In the WAR file, I'll have web pages, classes, and some configuration files. That's again a very boilerplate WAR file. So what I'm recommending is, I think one part we need to understand is refactoring your existing services to microservice has to be an evolutionary architecture. You can't say, I'm going to throw away my existing application and I'm going to start brand new, and then I'm going to start building a microservice-based architecture. Yes, you can do that if you have time, resources, money, and all those things. I don't, so my customers don't. So they are always looking for an evolutionary approach. So then what I'm recommending is, and hear me out, and this is the first time I'm presenting these slides in my thought process. So hear me out. So take a WAR, convert it into an year. So what you're doing is, you are refactoring your web pages, classes, and config files into functionally decomposed modules. Now remember, in a year file, well, a WAR file is one big monolith. Year is a bigger monolith as well, but in an year, you have lots of different WARs which are possibly functionally decomposed by themselves. You will still have some jar files which are possibly shared across these guys. You will still have a web module where you will have a web pages and configuration files, but that's sort of the first step that I've started doing. Now, how do I take a WAR and refactor it into an year? So, this is ugly. Okay. Well, so what I did is, this is existing. I should have animated this. Sorry. This is a WAR file structure. So ignore the red circles and the black arrows for now. I literally built this slide like an hour ago. On the top, what you're seeing in this red circle are all the web pages. This is a WAR file, okay? In the webinif classes, I have all my packages. As I was saying earlier, remember, all of these are functionally decomposed packages already. So I have REST, points, JSON, entities, client. All of these are functionally decomposed packages already. And then I have a template.xhtml. So that's my very classical WAR file. Now, if I've been able to convert this into an year file, if I look at my corresponding year file, well, all my web pages, effectively, or at least the entry-level web page, it goes into my Movieplex web module. So that's my WAR file. So I put it in there. The corresponding page, so like batch and batch here. So all those classes, because they're functionally decomposed, and remember, the app has to function by itself. So the batch class and the batch pages, I put them together in a WAR file here. Similarly, booking and booking web pages, they go in the corresponding WAR file. So I got different WAR files which are already functionally decomposed. This is a template.xhtml. Now in Java E7 terminology, we have this concept of a resource library contracts. So template, basically what that gives you is the ability to apply the same set of templates across your WAR file. It's basically a library, and it's a predefined data format. So I bundle this template and my corresponding CSS, which are not shown here. Yeah, my CSS files are not shown here, but template.xhtml and CSS are bundled up together in the contracts jar file. So I put them up here. My entities are here. My JSON utilities are here. So I put them in the lib so that they're accessible by all the WAR file. So that's sort of my first step, where I take a WAR file, refactor it into an ER file. Now, at any point of time, you're welcome to skip the step and say, for example, jump straight to state 3, where I'm taking an ER and converting it into a WAR file. So remember here, this is running as one unit. So ER is still deployed in my wildfly container. I'm still having the common database. There is still some sharing going on between these files. And now I'm saying, oh, by the way, now run them as separate WAR files, maybe in the same wildfly container, because those are already functionally decomposed. So test it out. Let me start throwing them as independent WAR files. The biggest challenge that I really had was in my monolith. I had, say, index.xhtml. That was my entry point to the interface. As I said, all the services are up, all the pages are up, all the CSS are up, all the classes are accessible, so I can use any class that I want to. But when I started refactoring here, the biggest challenge for me was, oh, you know what? No, this is living in a different service. So I need to define a contract for it now. I can't just use a class just like that, because it's living in a different microservice now. Or entities. Entities need to be used by all of these services. So where do I place them? I need to place them so that they're accessible by all the classes. Should I bundle entities into all the WAR files, or still make it accessible? So things like those, kind of started coming along. So at this point now, I have my ER file now splitting back into WAR files. Each of these WAR files are potentially running, as independent WAR files, and then my interface is basically composing all of these different services together. From here, what you can do is you can say, hey, instead of taking Wildfly as an application server and running in the same application server, I could easily create, for example, a Docker image. And I'll talk about Docker in a second. But effectively, I can create a Docker image. It's a WAR file living somewhere in my Nexus repository. From the Nexus repository, I'm going to grab that WAR file. I have a pre-built image of Wildfly, jboss/Wildfly. I'm going to pick that Wildfly image. I'm going to drop this WAR file in there. And that's how I'm going to compose my application. So these are really each independently functionally decomposed services running in their own container. And here I'm even showing my database even running as a Docker container, for instance. And once you have done that level, then each of your Docker container could independently scale very well. On the x-axis or z-axis, sharding or horizontal scaling, whatever you want. Now, one of the concepts with microservices, people talk about, does it really mean pushing the complexity around? Yes, it does. Because effectively, you're saying all that complexity of a monolith, etc., once you have functionally decomposed the app. But remember, we were looking at it, how I had to make sure which jar sits where. And so there is some code which has to be duplicated as well. So effectively, the plumbing that you're providing, that you're adding to coordinate those microservices becomes confusing. That's where you're pushing the complexity around. So what we need in that case is what is called as no-ops. Now, no-ops is a movement which was coined around 2012, 2013, more like 2013-ish. And here it's talking about these are some of the aspects that required for a microservice to be successful. So for example, service replication. Who's going to handle service replication? Yeah, service is running in a container, but does that mean I'm going to write my own script to monitor the container? And if the container goes down, should I bounce it? Well, that's where things like Kubernetes, which is a project by Google and heavily contributed by Red Hat, is very useful. It allows you to schedule your containers very easily. How about dependency resolution? What if my service how I'm going to resolve where my service is living or service discovery. How I'm going to do that. So Nexus is one way by which you can do dependency resolution, but this should be more like dependency or service discovery. We talked about how failover has to be a key feature of your microservice architecture. So that's where if you have read the book Lean It, it talks about this circuit breaker pattern. Now remember, go back to the Netflix use case we were talking. Thousands of servers running across across the world on AWS. What if a thing you're pinging a service, you wait till you get a response? Can you do that? No. What if then you have to build a circuit breaker pattern? Circuit breaker is basically like circuit breakers in our home. If the thing is going too high voltage or too low voltage, the circuit will trip, and that's what you're going to do over here. There are libraries available in Netflix open source GitHub repository, which allows you to implement circuit breaker pattern, which says if you try to ping a service and it's timing out, increase the time after which you're going to ping the service. Similarly, keep increasing, and once you have pinged the service and the service is responding back, then reset the status back. So that's kind of a cool aspect of this failover. Resiliency, Hystrix allows you to define how your code can be more resilient. What are the if the service particular fails, is there a failover mechanism? Where can I go? If this service is not available, is there a default page that's going to come back and show that this actually works? I was talking to a friend at Amazon, and I was asking him, when you guys went to the microservice-based architecture, what is one thing that you would really invest in? And they said, this is going to be the biggest thing for us to invest in. Monitoring, alerts, log stash, and stuff like that. Because that's what allows us to identify how our entire application is doing. You may do monolith, whatever it is, but this is where their biggest investment is, and they would recommend people to do that. I'm going to skip this graphic. So microservices is not a panacea, as I said. This definitely adds complexity because now you're running in a distributed systems. So libraries like Hystrix, or Netflix open source libraries, resiliency, failover, all those need to be taken into consideration. It does require a significant operational complexity. So a very high level of automation is very, very important. Because if it's not automated, then you can do your continuous deployment and things like that very easily with this. With the monolith, when your monolith comes up, everything is up. It takes a while, but everything is up, and then it's ready to go. But with microservices, what if a service is coming with a new version? What if you want that new version to be effective for other services? So there is some sort of a manual coordination or a tool coordination or a Jenkins coordination is required, or a deployment pipeline needs to be built, which will allow you to coordinate deployments across those different services. Now, when you start building a brand new application, and this is sort of a catch-22, when you start building a brand new application, do you right away start with microservice? Probably not, because there's a lot of infrastructural investment that is required to build a microservice. Understanding those libraries, using those libraries, and making sure you start seeing benefit of those. You won't see a benefit of a microservice till you have a few services really collaborating with each other. So then you say, oh, you know what, never mind, I'm going to start with a monolith application. So you start building a monolith application, and then your monolith application becomes too big, where you say, oh, you know what, I cannot refactor into microservice. So I think that's sort of a catch-22 you have to think about yourself, where you're going to get that investment from, because there's going to be a slower ROI to begin with. Specifically in the early days when you're investing into, how I'm going to build that operational complexity, automation, and things like that. So we talked about, running those services in a container. So how do I see this running? Well, the way I see this is how each service could very easily run in a container. Now, there are a couple of container technologies that are prominent. So Docker and Rocket are the two prominent ones. Docker is definitely the more heavyweight for now, more mature. So what is Docker? Well, it's an open source project and a company. So you can go to github.com/docker/docker. You can see it's not visible, sorry. You can see the number of stars are about 20,000. Number of folks are about 4,000. So it's a pretty popular project. It's basically used to create containers for software applications. Now, Java gave us Vora, write once, run anywhere. What Docker gives us is Poda, or package once, deploy anywhere. Because effectively, you can package your application once using Docker, and once you have packaged it, published it on a SaaS or a registry somewhere, anybody can download that image and run it exactly the way you wanted it to run. So the underlying technology for that, of course, is all written in Go. So this is a snapshot from the languages. You can see almost 90% is written in Go. It uses several Linux features, which were heavily contributed by, which were actually designed by Red Hat. So in Linux, there is a concept of namespaces. Just like Java packages, it allows you to give you isolation. They cannot interface with each other, and that's what Docker uses to provide that isolation. Your Linux also has this concept of control groups, which allows you to say how much memory should be utilized, how much hardware resources can be utilized, and Docker exposes that. When you run a container, at that point of time, you can say, I don't want this to be a resource hog, so just limit it to 128 megabyte RAM or half a gig of RAM, and it's never going to go beyond that. Union file system is a very key concept because what you start with a very Union file system is a very standard Linux technology. You start with a very core operating system. You want to write something on it, you cannot write on it. It's a read-only file system. When you want to write something on it, you basically write a layer on top of it. You want to do some operation on it, you write another layer on top of it. But effectively, you have multiple layers, and those layers are joined together using this union file system. And that's what gives you the idea that, okay, you know what? For a user, you get one single feeling, but that's sort of the internal detail, the way it works. And libcontainer, these are the four technologies. Libcontainer defines the container runtime format. So there are three concepts of Docker. One is the build container, so which one is the build aspect. So the way you run a container is using or defining everything that you want to do in a Docker file. The name is Docker file. It's basically a text file. But in the text file, you define what commands are required, like what operating system I want, what JDK I want, what app server I want, where is my war file, you define it. Docker, again, is very well suited for microservices because Docker has only one entry point. Just like your single responsibility principle, it can only do one thing. There's only one entry point. This is my most trivial Docker file. All I'm saying is from Fedora latest command echo hello world. So that's your hello world Docker file, for example. So if you have your Docker engine running, or on a Linux box, you have a Docker, you say Docker run this image, is going to download the Fedora latest image of Docker, and it's going to run that command over there. And that's it. It's just a hello world, and it runs really fast. You want to go a little bit more advanced. As I said, there's a concept of namespaces or derivatives. You can define base images, which are very, very heavily used for all different purposes. So this is a jboss/wildfly base image. In this base image, all I'm doing is I'm running a command. Now, by default, if I just say jboss wildfly, is gonna start up wildfly for me. But in this case, I'm overriding the command. I'm saying, oh, run. That means it's gonna override the command what was given earlier. I'm curling a war file into this particular directory, which is opt jboss wildfly standalone deployments directory. So all I'm doing here is I'm saying start up wildfly and copy this war file into the deployments directory. That means this app is going to be automatically deployed for me. So literally these two lines, and the jboss wildfly image is derivative of another image and so on and so forth. So the fundamental purpose of Docker is how you can have those derivatives using those base images very well. So what are the advantages of containers? Several, actually. Faster deployments, because a fundamental difference between, and I'll explain that in terms of containers and virtual machine, is huge. Containers really start in a matter of a couple of seconds, as opposed to a VM, which takes a few minutes to boot up. Because of isolation, because of namespaces and features like that are available in Linux, the containers are fully isolated and they cannot interfere with each other. So if one container goes rogue, doesn't mean the other container will also go rogue, because they are completely separate in that sense. Typical problem, if you want to ask somebody that, hey, this is my test is failing or my code works, and it says, hey, it works on my machine, I don't know what the environment issue is. With Docker, you can actually replicate the exact environment, because in your Docker file, you can say, this is the exact operating system, this is the exact JDK, this is the exact application server, this is the exact Nexus tag for the Maven or the war file, and you can reproduce it. So it gives you that replication of environments. No more, it works on my machine. With Docker again, because the images are maintained in a repository, you can start tagging them, and you can fall back on a particular version of image. Say, you know what? Okay, I'm going to download that particular image instead of the latest image. So there's a concept of snapshotting that is available. Each Docker can quickly, I was talking to a customer, I think 3 days back. They were talking about how they had to test their functionality against multiple database servers. Now, installing a database server is quite a nightmare task. And if you have to run it like on MySQL and Postgres and 3 versions of Postgres and then HSQL DB and all those and so on and so forth. So all they did was they quickly created those security sandboxes. They said, you know what? Hey, here are these 7 Docker images. Just fire up those Docker images, run the test, and throw them away. Because then they know it works against that Docker image, and they knew exactly what version it is going with. So that was one big advantage for them. I talked about how it can allow us to limit the resource usage. In a microservice world, again, it's going to be very critical because you don't want your microservice to hog the entire space. With the Docker file, you can clearly define how the dependency mechanism is going to look like. The sharing is very easy. So once you create an image, you can push it to a Docker hub, and then you can say, you can download my image, you can download my image. They're all publicly available anyway. So there are some pros to Docker, which gives you extreme application portability. How you can take a container and share it with others. It's very easy to create your own derivative and work with those derivatives. So for example, we looked at jboss/wildfly, how easy it is to derive from that image and add your own functionality. And it's a very fast boot on containers, so it really allows you to simplify your entire development cycle. However, Docker is a very host-centric solution. You can run those multiple containers very easily on a single host. Now, Docker has Docker Swarm, which they announced recently at DockerCon in last year, November, but it's still a very host-centric solution. So that's a single point of failure. That's not going to work for me. Now, you're spinning up all these different Docker containers. You need something on top of that to do a higher level provisioning. That's missing from Docker. Again, Docker Swarm is the goal to fulfill that, and we'll see how that evolves. And with Docker, there is again no usage tracking and reporting. So those are the missing pieces from Docker itself. So meet Kubernetes. Now, Kubernetes is an open source orchestration system or scheduling system for Docker containers. Now, today is designed to work with Docker, but hopefully in future it will work with other containers also. But Docker is sort of the primary container technology anyway. The coolest thing about Kubernetes, which I like, is how it allows you to say, specify the desired state. Now, how many times, you have managed a server where you say, oh, you know what, I need 3 instances of my application server running. I'm going to write my monit scripts, which is going to monitor. If a server goes down, I'm going to bounce it again. Or if an additional server is spun up, I'm going to kill that server. Now, that's the beauty of Kubernetes. To Kubernetes, you say, I want 3 instances of my server, and Kubernetes does all the dirty job for you. It makes sure there are exactly 3 instances. If there is an additional one for some reason, it kills it. If there is a less one which is there, it spins up an extra one for you. So that's what makes Kubernetes so powerful, because you are just defining the desired state, and Kubernetes maintains it for you. And that's what we call as self-healing in Kubernetes language. It automatically restarts the containers as well. It works across multiple hosts. So you can start up a Kubernetes cluster, which could run across multiple hosts, and it works with multiple VM providers. So you could run it on, for instance, on Amazon, Google Compute Engine, VMware, Vagrant, you name it, all different sorts of providers. And it allows you to replicate those containers as well. So I'm going to quickly go through the concepts, because I want to show the key part on how we see these microservices going to be composed with each other. So pod is a co-located group of containers. without getting into too much details, typically the design pattern that we are seeing more and more people are using is typically a pod is one container. In certain cases, you may say, I'm going to bundle up containers together. So for example, a web server and something that along with web server is pulling some data from the file system. Those two are logically related. The idea is they share a volume and share an IP address. Now, the IP address of the pod itself is ephemeral. It is assigned an IP address, but Kubernetes holds the right that if a pod goes down, it can start it up on a different container and assign it a completely different IP address. So that makes the pod really inaccessible to anybody in the cluster. That's where you say, I'm going to have a service in front of a pod, which is the IP address that can be used by anybody. So you define a service, and service also acts as a load balancer. So for example, you can have multiple pods being front-ended by a service. This has an IP address that is fixed and is reusable within the Kubernetes cluster. Now, typically, you would not create a pod by yourself. You won't say create a single pod. You will say, I want to. This is a redundant concept to me, but bear with me. You would say create a replication controller. In the replication controller, you will define what your pod recipe is and how many replicas you want. So, for example, your replication controller could say 4 replicas of a pod, and you define the image as a cookie cutter recipe. So it's going to spin up 4 instances, and then you will front end it with the service. And all of these, which pod belongs to which service and all that stuff is maintained using labels. So quickly, if we see, in terms of Kubernetes, really, the pros are it allows you to manage all related Docker containers as a single unit. It allows communication across multiple hosts, and it automatically allows you, automatic or manual scaling of pods. So it gives you scalability, monitoring, and all of those within the Kubernetes cluster. However, it is missing several things. As a Java EE developer, remember we talked about I'm taking my existing Java EE application and refactoring it into microservice. So I care about a Java EE application. How do I take that Java EE application, do a full build, deploy, manage, promote without worrying about the fact that, underlying this might be a Kubernetes Docker thing. You go figure out the details, because Kubernetes requires extensive configuration files. Am I supposed to write it? Is somebody going to generate it for me? That's not going to work. How do I port my existing Maven projects into Kubernetes configuration? How do I do my DevOps? How do I do my multi-tenancy? None of this is available in Kubernetes today. So my typical application, if I have refactored, functionally decomposed it. Now this is not truly functionally decomposed. I shouldn't be saying that. But I could have, say, let's say, imagine from Kubernetes perspective, I have a database running, I have a Java EE service running, I have a messaging service running, I have a web service running. Okay, those are all services back-ended by. I'm showing only 2 pods, but could definitely be multiple pods. That's my service, and that's what we are defined as an application in OpenShift terms. Now, OpenShift is Red Hat's open source PaaS platform, and in OpenShift, we define this concept as an OpenShift application. OpenShift v3, which is scheduled to launch later this year, is completely using Docker as a container technology and Kubernetes as the orchestration framework. Now, at the bottom of OpenShift v3, we use RHEL 7.1 and Atomic. Now, Atomic is designed to run containers as a first-class citizens. On top of that, the container technology is Docker, cluster management is Kubernetes, and that's where OpenShift provides user experience, for example. It says, hey, you need full tooling support, you need those utilities which would allow you to consume the Maven project and generate an application which can then talk to Kubernetes configurations and all those things. So Kubernetes will, the OpenShift v3 will provide entire experience on those lines. So that's pretty much my last slide, and I have about a minute more maybe. But effectively, from the JBoss side, from the Red Hat perspective, I think we have a whole variety of tools that allow you to build your microservice. Now, whether it's Eclipse, whether it's which provides integrated tooling with OpenShift, whether it's JBoss EAP, which provides a first-class, wonderful platform for Java EE applications, whether it's mobile applications, whether it's Apache Camel for your integration, whether you want to replicate your data, whether it's persistence, whether it's testing, whether it's polyglot environment using Vertex. So I think we have a whole variety of tools that we offer from Red Hat perspective that should make your life easy. I think that's about my time. It says 5:20 here. Is there a session after this? We can keep chatting otherwise. There is a session? Oh, okay. Well, I guess that's the end of it. I'm going to be outside in the hallway. If you have any questions, I'll be happy to take them. Thank you so much.